Hello everyone. Thank you for attending the talk. So today I'm going to be presenting to you the work that I'm doing during my PhD. It revolves around the design of magnetic resonation reality. I'm going to begin with the brief context of the project to explain to you the how and why of the project. Then I will be presenting my results. First, I will be presenting the production results of our heating agent, which is iron wool. After that, I will be presenting the results the experimental results that we got with our magnetic pilot reactor and the numerical results that we got with our simulations. And after, I will finish with my main details. So the context of the project. First of all, what is induction heating? So induction heating is an electrical heating method that's been used for around 60 years now in the industry, so it's pretty mature. You can find it in a lot of industries, and for example, in some domestic uses as well, such as industrial stoves. So as I said, it's an electrical heating method that works, as you can see here in this schematic. We're going to be creating a magnetic waves. Magnetic waves will then be absorbed by magnetic material and transformed into heat. So first of all, the big advantage is that it's electrical, so we can power it with renewable energy sources. It's no contact, since we just have to create the magnetic waves, and then they will be absorbed by our magnetic material, and it's targeted. So for example, if in our core we put two types of material, one which is magnetic and the other non-magnetic, we're going to only be heating our magnetic material. And it's fast and dynamic heating, so we can have really fast heating of hundreds of degrees per second. And it's dynamic because, for example, if you want to control the temperature, we can control it really precisely. And also, once we stop the magnetic waves, our heating will stop also directly. And lastly, it's really high in energy efficiency. We can get induction processes with energy efficiencies up to 95%. The main idea in our lab and in other labs right now is to use induction with catalysis. Heterogeneous catalysis. So the idea is to use induction in order to heat our catalysts directly inside the reactor. So we would be starting from the hot wall reactor model, where we're heating the walls of the reactor and transferring energy from the reactor to contents inside and then into our reaction medium to the reactor, where we bypass our reactor walls and we directly heat what's inside. So this type of reactor model, of course, will give us a lot of advantages, such as faster startup times, since we're only heating what's important, which is the catalyst. Lower energy consumption, better reaction control, lower secondary reactions, and better security. And the main idea in our project is to use this type of reactor in order to apply it for power-to-gas applications. So what's power-to-gas? Really briefly as well. So as you all know, right now we're more and more dependent on renewable energy. But the main drawback with renewables is that they are intermittent. So we're going to have some period of overproduction, and we have to find ways to either store or transport this overproduced energy. And in power-to-gas, the idea is to transform this energy into chemical compounds which are energy carriers, such as CH4. So by doing, for example, this reaction. The methanation, CO2 methanation reaction. And what our aim is to create or to develop an induction heated methanation reactor, which will be used in order to do the reaction, and to have a reactor that is dynamic, local scale. First of all, dynamic because the energy source is intermittent, local scale, and of course, good energy efficiency, and that can produce cheap CH4. So the first thing we did, the first challenge, was to have a catalytic bath that's not expensive. Because in order to do scale up at industrial scale, you need to have a cheap catalytic bath. So we chose to use iron wool. So this is iron wool. It's something I guess we've all seen before. It's something that we can buy at the supermarket. It's commercially available. It's pretty cheap, and it has really interesting physical and magnetic properties. So it's heating under induction waves. It's really good. And we've been using it in our group, so in the University of Toulouse, to do a multiple magnetically induced reactions, such as the methanation of CO2 methanation of CO, the reverse of the gas shift reaction, some other hydrogenation reactions. But in order to optimize its use and to be able to do some moderation installation afterwards for some reactions and reactors, we had to do a little bit of a deep dive into the mechanics that are used in the heating of iron. And a little introduction here. For induction heating, we're going to be seeing mainly two types of mechanisms for the heat. The first is the eddy currents, which we can see here a little bit. And we observe this mechanism in bulk materials. So anything that's, for example, a big slab of metal, or with the induction stove at home, put like a plate to heat it on the induction stove, we're going to have these eddy currents that are created. And the other mechanism is hysteresis losses. These cycles, hysteresis loops or losses, they are mainly observed in nanoscale materials. So, for example, in catalysis, we're using nanoscale catalysts in heating it with induction heating. This is what we are going to be observing. In order to study our iron ore and to determine how much it heats and the mechanisms that are taking place, we have mainly two types of experiments. The first is the classical thermometric measurement, where we would apply magnetic waves onto our samples for a set time period. We would measure the temperature increase, and then, of course, we can measure the amount of heat that's being created. And would so calculate something that we call the SAR, which is specific absorption rate for material, and it's watts per gram of silicon. And also, we did some hysteresis cycle measurements. In this case, we would apply the magnetic field onto our sample, and we would measure the magnetic response of the sample, as we can see here. So we have a system magnetization function of the applied field. And so we're going to have these cycles. And the heat that's being generated with this mechanism, the hysteresis cycle mechanism, can be calculated from the surface area of each cycle. So the bigger the cycle is, surface area is, the more heat is being generated. The first thing that we want to study was the effect of the diameter of the strands of Fe wool on the heat. So commercially, we found these three different types of Fe wool: the super thin one, thin, and medium. And here we have the average diameter of the different samples. And as you can see, the bigger the diameter is the more heating we can have. For example, for the biggest one, we have around 700 watts per gram, maximum value of SAR that was measured. And for the super thin one, we have around 160 watts. The second thing that we studied was the effect of the strand length. And to study this, we took one really long strand, it was around 8.5 centimeters. We did the measurements, calorific data. And then we cut it into 8 smaller pieces, 16, and then finally 32. And what we observed is that when we went down with the strand length, also the heating was affected, and it also got lower heating hours. After that, so as I said, we mainly are going to have two heating mechanisms, either the eddy currents or hysteresis. And since we did some hysteresis loop measurements and total heating measurements with the calorific measurements, we are able to identify which mechanisms are dominant in our samples. And here, for example, just to verify that our measurements were correct, we took some nanoparticles. And in nanoparticles, we should be observing 100% of heating from the hysteresis cycles. And that is what we did solve our measurements. After that, so for the iron ore, what we observed is that, for example, for the biggest strands, we have around 90% of the heating that's coming from eddy currents and 10% that's coming from hysteresis cycles. And for the super thin one, we have around 60% eddy currents and 40% hysteresis cycles. Later, we're really interested in studying the effect of adding functional surface layers on top of the iron. So for catalytic purposes, it's really interesting to be able to add functional layers. For example, for the iron ore, if we add a nickel layer, it becomes a catalyst for the methanation reaction. If we add a silica layer, it can help to protect our iron ore from if we have any like acid or base reagents or products or reaction medium. And so we studied the naked FE mode, the regular one, and then one with the silica layer, one with nickel layer, and one with both nickel and silica layer. And what we observed is that the FE wall with no layers added had the best heating power, followed by the one with nickel, and lastly, the ones with silica or silica and nickel at the same. To better understand what's happening, we did the following measurements. So we took FE wall with nothing on top, and then FE wall with silica. And we did one total heating measurement and one hysteresis cycle measurement. And what's really interesting is that for the hysteresis cycles, we have the same measurements for both the regular iron mold and the iron mold with the silica coating. So what we can see here is that adding this coating has no effect on the magnetic properties of iron mold and has no effect on the hysteresis cycles. But it has a big effect on the total heating. So what we can conclude is that it has a really detrimental effect on the generation of eddy currents. And we think it's due to the fact that silica is no conductor. And so when we add it on the surface layer of our iron mold, it's gonna hinder the creation of eddy currents, and thus that's why we're seeing this detrimental effect on the total heating of our samples. And the last thing that we wanted to study was the density of our bed and its effect on the heating power. Since the density of the bed is something really important and that we can change in our reactor. And as you can see, when we were increasing the weight of packed iron ore in a specific volume, our SAR was going down. And for the total power that's being generated, it hits a plateau. So that's something really interesting. And to understand why this is happening, we did some two-dimensional simulations. So here, what we have, we're going to have a coil that's generating magnetic waves. And in the first simulation, we just put one strand of iron ore in the middle of it. And we register around 1.5 watts of created heat. But if we put more strands, the middle strand, so the same one that's here, it's the same size and properties, this time it's going to be registering around 0.6 watts. So we lose more than 50% of its heating power. And what's happening, we think, is that the other strands are creating some type of screening effect and hindering the absorption power or heating power of strand that's in the middle. And why is this really important? Because if you imagine doing any type of scale-up later for the reactor, we really have to take into consideration that the heating is not homogeneous radially. So we're going to have a heating that's stronger on the outside radius than in the middle of our reactor. So that's not really important. The main takeaways for this part is that the iron ore is great as an agent. We have stars that are really high, and it's really cheap and easy to use. The main geometrical factors to take into account are the length of our strands and width, and also adding functional layers can have really beneficial effects for catalysis use, but it also has bad effect on the total heating of our strands. And also radiation of the heating is observed, which should be taken into account when scaling up the process or doing any simulation of the issue. Now I'm going to briefly present the induction heated methanation reactor that we were working on. So here in the picture, this is the pilot reactor that we worked on. So our pilot reactor is a simplified schematic. We can work with two different gas compositions. It's either with pure CO2 and H2 or with biogas and H2. So biogas is going to be roughly 60% CH4 and 40% CO2. Sorry. And 40% CO2. The reactor, here you can see it, it's made out of glass, so no magnetic material. And inside of it, we're going to have a bed, which is made of iron ore and nickel deposited on alumina as our catalyst. And so, since the reactor is made out of glass, it's non-magnetic, the magnetic waves will pass through it directly into our bed and will be absorbed only by the bed heater. So, we're only going to be heating. The operating conditions that we worked with for the pressure was between 1 and 10 bars, temperature between 250 and 450, the flow rate was between 2 and 4 liters per minute, and as I said, the gas composition, we have these two configurations. we had some really good results with our pilot reactor. First thing is that we were able to get conversion rate of CO2 of around 95% for both cases when we were working with QCO2H2 and biogas H2. With the selectivity 100% of CH4, so we were not producing any CO in the experiments. The startup time is extremely fast, especially if you compare it to traditional methanation processes. That startup time is around 40 seconds. The energy efficiency is close to 67%, and here I should just add that 67% is the maximum, the maximum for the CO2 methanation. And also we were able to have dynamic and flexible reaction control thanks to induction heating. And so we were doing some tests where we changed the inlet, we changed the composition, etc. And with induction heating, we were able to dynamically control our reactor and avoid any runaway or any heat. So in order to better study this, our reactor and do some optimization and maybe later scale up, we decided to do numerical reactor models, so to do some simulations. And our first model is a heterogeneous 1D model where our values are going to be changing in the z-axis only. And this is the lab that we modeled as well. So we're going to have the iron mold and then our catalyst, iron catalyst. And you can still see different temperature profiles, the gas temperature, the catalytic bed, and then the reactor. And of course, heat is generated directly inside the catalytic bed. And we use the some measurements that I already presented in order to be able to calculate precisely how much energy we're creating inside the bed. And the main heat generation and transfer calculations that we use. First of all, of course, we're going to have the first conduction between the gas flow and the fuel. And this is pretty important because we're generating the heat inside the fuel directly. Then we're going to have the first conduction between the gas flow and the catalyst, conduction between the gas flow and the reactor walls, the conduction between our catalytic bed and the reactor walls, free convection between the reactor wall and the outside, and this is the only way of cooling down that we have in our reactor. So it's kind of a quasi-adiabatic case. And of course, the heat generation via magnetic heating. And we shouldn't forget the heat generation of the reaction because the methanation of CO2 is a highly external reaction. So we're going to be generating a lot of heat from the reaction. And this is the typical simulation result. So what you're looking for is calculating the profile of temperatures as well as the gas composition. And in our simulations, we are trying to change the field, change the quantity of the catalyst, quantity of iron wool, the power of heating, etc. And trying to study all of these parameters and how our reactor is changing, how our outlet, like the field at the end, is changing with these parameters. So now we finished all the validation for our model, and we have some preliminary simulation results that I'm discussing now. So first of all, we developed the numerical model to predict with accuracy the experimental results that we got with our pilot reactor in terms of conversion rates, startup time, selectivity, and temperatures. With the simulations, we were also able to identify the presence of hotspots, which we were seeing in our pilot scale reactor, but we weren't able to really identify where they were being created. And using the reactor, the numerical model, we also were able to identify that working at 10 bars without any type of cooling mechanism for the reactor is not feasible because we're going to have some really high hotspots and the risk of overheating the environment. So the main takeaways of our work until now is, first of all, magnetic heating is a promising electrical heating method for heterogeneous catalysis and electrification of these type of processes. Iron is a really good, cheap, and efficient heating agent for magnetically induced catalysis. And our result had optimized its use in catalysis and any simulation or modelization work. Induction heating is great fit for power to gas application, considering its high energy efficiency, fast heating, and adaptability to alternative energy sources. And lastly, more work is needed to optimize the design of the reactor and in order to scale up the process. Thank you. Any questions or?